Alright, so this is my third and final lecture on the photoelectric effect. Okay, so to establish what the experiment was again, we had a metal with some electrons in it, and we are going to kick these electrons up and out of the metal using light that was going to strike the metal and basically run into the electrons and kick them up and out. And we determined that this light had a certain energy E, and this energy is related to both its intensity and frequency. Okay, so let me talk about the actual observations of what actually happened when they did this experiment. So, first off, I want to talk about what current is. So current is just measuring in the metal how many electrons are up and outside of it flowing along it. Basically, that's what's happening. When you kick an electron up and out, it joins a current of electrons flowing along. So this is just measuring how many electrons we have. And we remember frequency was one of the ways we could control the energy of light. Basically, you were varying the color of your light bulb and seeing how much current you get. It was very interesting because what was actually observed was that up until a certain frequency there was no current, and then the current linearly increased, okay? And why is this? So this is fascinating because this zero region, I mean, that light still has energy. For example, when you shine red light on this metal, you might see no electrons. You have to wait until a certain point before you see any. And this is a really important result. Let me elaborate why this is so important. Okay, and the way we're going to do this is now we're going to look at the other measurement of intensity versus current. Basically, how many photons do you have? And when they did this, you got a normal result, sort of. Say they shone blue light on, and they just saw that as they cranked up the intensity, the current went up. Kind of like what we expect, okay? You're increasing the energy, it goes up. But the weird part is say they shone red light on this, what they saw was just a flat line. No current at all. And now I'm going to discuss the physics of how from these two graphs you can conclude that light must come in individual little chunks called photons, which is exactly what Einstein did. Okay, so I'm going to draw our electrons down here. These are just two electrons in the metal. And this little region here, the electrons have to get up into here to start flowing along in the current, okay? And now we're going to have our incoming light, and we're going to have a red light hit this, and we're going to have a blue photon hit this electron, okay? Now, what ends up happening is the blue photon has more energy, so it kicks it all the way up and out. The red light only kicks it this far, and then basically what happens is the electron hasn't gotten up here, so it falls back down. And we can shine in all the red light we want. The thing is they only interact with the electron one at a time because they're in little chunks. One chunk hits it, kicks it up, it falls back down, the next chunk hits it. You can't have two chunks hit it at the same time. And Einstein, looking at this, had this realization that that's why we see no current if we go below a certain frequency, because the energy of the individual photon interacting with the individual electron is determined only by the frequency. Okay? And he actually made a measure of this energy. This is a very famous equation, that energy of the individual photon equals h nu, where nu is the frequency. Okay, so this is the frequency, and this is some proportionality factor. And this is actually called Planck's constant. Okay? And I just want to emphasize, I'm going to work through some problems in another lecture with exercises for this, that this is a huge result. This is the big conclusion, that light must be quantized into photons. And these photons come in energies h nu. It's related to their frequencies. And really, this is a bigger thing in quantum mechanics. In general, the frequency of something is proportional to the energy, and everything has frequencies, even electrons, okay? And this is breaking away from the classical model that intensity is also just a general measure of energy because you can't apply it to individual particles. Okay, so I encourage you to do the exercises. I know this is a lot of material, but in the exercises, I think you'll get a feel for how this all works together to produce the photoelectric effect. And you'll get a feel of why those graphs need to look like they do because of this.